Hello everybody, welcome back to the session on Natural Language Processing 1. Last week we started a new module called Computational Morphology, in which we said there are 4 components: morphology, morphological parsing with finite state automata and 2-level morphology, and finite state transducers. We completed what morphology is, what is inflection morphology, and what is derivation morphology. This week we are going to look at morphological parsing. Why do we need morphological parsing? And we are going to look at human morphological processing as a basis for developing morphological processors. As part of morphology, we deal with 2 major processes: analysis and generation. Given a particular word, morphology helps us to analyze the word into its components. That is, if you have a word like leaves, it can be analyzed in 3 different ways. Firstly, the word leaves can be analyzed as the word leaf, as the stem, and its parts of speech, then the morpheme plural. Secondly, it can be analyzed as the word leaf, which is a stem, and leave as a noun and the plural morpheme. Finally, the word leaves can be analyzed as the verb leave and third person singular inflection on it. That is, the word leaves has 3 different analyses. In other words, what we are saying is the word leaves is ambiguous between 3 meanings. The other process is generation. That is, given a word, its category and the inflection or derivation of what we would like, what we want, then we will be able to generate the words. So if you are given a word like hang, which is a verb with past tense morpheme, we can generate 2 words, hanged or hung. In fact, both of them mean the same. That is, the word hang as an irregular verb can have hung. We can also have hang as a regular verb taking ed as the past tense morpheme. That means there are 2 surface forms for the same word. Now let's look at allomorphs. In fact, when we are analyzing the words, we have said S as the plural marker, right? S as the morpheme, but the morpheme may have different forms on the surface. That is, a morpheme may realize in different forms, and those forms are called allomorphs. So a morpheme is an abstract element, whereas allomorph is the realization of a morpheme. Let's take an example and see what we mean by morpheme and allomorph. When we say the plural morpheme in English, right? When we say the plural morpheme in English, what is it? Is it S? Is it sir? Or is it the? Or is? Plural morpheme of English may be the, and it is realized in 3 different forms. These 3, sir, the, and is, are allomorphs, and the relation depends on the word. The plural morpheme the is realized as sir when the word ends with a voiceless sound. The word cat ends with the sound t. T is voiceless, so the plural is sir, cats. When the word ends with a voiced sound, it is the. So you can see dogs. So the word dog, g, is voiced sound, so the allomorph is the. You pronounce it as the. If the word ends with s, or what we call sibilants, s, z, sh, zh, ch, j, when a word ends with a sibilant, the plural allomorph is. That is, the plural morpheme what we call plural morpheme, which is abstract, on the surface realized as three different allomorphs, either sir, the, or is, depending on the context. So when you're doing analysis, if you look at cats, then sir is the plural morpheme. When you say dogs, the is the plural morpheme. Buses is the plural morpheme. Right? So while doing morphological analysis, we need to look at allomorphs. Now let's look at what parsing is. Parsing takes a surface input and identifies the constituents of the input and the underlying structure of the input. Parsing can be at syntactic level or at morphological level. So when it is at morphological level, it is morphological parsing. In morphological parsing, a word is taken as input and it's analyzed into the stem and affixes, and the parser identifies the relationships between the stem and affixes. That is, for example, if you take a word like leaves, which we have already seen, this will be parsed as follows. It will be parsed into the word leaf, and leaf is a noun, and the S is a plural morpheme. So plural feature, basically it's a plural feature which is given to the word leaf, so it becomes leaves. Similarly, it can be analyzed as leave as a noun and the plural morpheme, or leave as a verb and third person singular. So it is not just analysis of the word into its constituents, but parsing also tells us how they are combined with each other. That is, parsing shows relationship among the constituents. So when you look at the word immovable, the word move is the stem. First, move attaches to able, or able attaches to move. Then the negative prefix attaches to movable. It is not the other way around. That is, im doesn't attach to move first and then able, because there is no word like immove. There is a word movable, and from the word movable, im is derived. So the derivation process is also given in parsing, and the derivation process, we are representing it in terms of bracketing. So what we are saying is, the word move is the stem, we have put it in one bracket, and then we have attached able. So move and able are together in another set of brackets. Then im attaches to movable, that becomes one word. So this can also be represented in terms of trees. So move attaching to able and immovable attaching to able. That is parsing and morphological parsing. Why do we need to parse words? We need to parse words to develop spell checkers. When we are typing words, we make mistakes. And if there is a spell checker, it's easy for us to understand where we went wrong while typing. So spell checkers are a very useful tool, and morphological parsers help us in developing spell checkers. And spell checkers also tell us whether a particular word is a legal word or not. For example, is munchable a legal word? Spell checker will be able to tell us whether it is legal or not. Similarly, we need to parse words to identify parts of speech. Parts of speech tagging is a very important component of machine translation, where each word in a sentence or each word in a text has to be identified and a parts of speech is assigned to it. Right, that is, we need to identify the parts of speech of the word. A morphological parser will help us in identifying parts of speech. For example, if you find a plural morpheme or a particular word, then that word is a noun. Or if you find a past tense morpheme on a particular word, that word is a verb, right? So word parsing or a morphological parser helps us to developing parts of speech tagger. So we can identify parts of speech, and parts of speech tagger helps us in sentence parsing or machine translation and so on. Parsing words is also necessary for identifying a word's stem. When we parse words, we identify the stem. When you identify the stem, then we know what the actual mean, what actual the word is. That is, what particular meaning it has. Depending on that, we will be able to retrieve information. What is necessary for morphological parsing? We need two kinds of knowledge for morphological parsing. One is spelling rules, the other is morphological rules. Spelling rules because we parse texts, particularly written text, then we need spelling rules. And we need morphological rules to get to develop a morphological parser, because morphological rules will help us separate stem from affixes, and we know the stems, then we know the meanings of the words. Spelling rules tell us that English words ending in Y are pluralized by changing the Y to I and ending in ES, right? Or morphological rules tell us that a word like fish has null plural, and that plural of goose is found by changing the vowel in the middle, that is becomes geese, etc. So we need two kinds of knowledge for developing a morphological parser. But why do we need to do morphological parsing? In fact, we have already hinted at it. We need to do morphological parsing for information retrieval, for machine translation to realize for words. For example, the French words va and aller should both translate to forms of the English verb go. So when you're translating, you may find in French two words, va and aller, but both of them mean the same word go in English, right? So we need to process, we need to parse the morphology of the words. And then we also need morphological parsing for recognition of words and non-words. What is a word, what is not a word? So if Miss Clam, is that a word? No. How do we know? When we do morphological parsing, we'll know there is no stem as clam anywhere in the lexicon. Similarly, a word like anti-undoggingly doesn't exist in English, right? So morphological parsers are helpful in recognizing words and non-words in a particular text. What do we need to build a morphological parser? We need three components. One is lexicon. Lexicon, which consists of stems and affixes. Along with stems and affixes, we also need the information about each stem, that is, what parts of speech that stem belongs to. If you have a word like cat as a stem, then it should have the parts of speech that it is a noun, right? So lexicon gives us stems and affixes along with the parts of speech information. And then morphotactics. Morphotactics is the structure of words, the rules related to structure of the words. So when you say morphotactics of the language, we know how morphemes are affixed to a stem. That is, a plural morpheme follows noun in English. In fact, we have already seen in a word like immovable, able attaches to move first and then im attaches to the word movable. So that structure is governed by morphotactic rules. So morphotactics is necessary for developing a morphological parser. Then we also need orthographic rules, because we deal with written texts where how spelling changes when a particular affix attaches, or when a particular suffix attaches or prefix attaches, etc. So for example, if you look at in English, when you have a word like logical, the negative prefix is in, but when in attaches to logical, because the stem uh, begins with the sound l, the sound n in the prefix changes to l, that is in becomes ill in the context of l. So in plus logical, illogical. Similarly, in plus recoverable becomes irrecoverable. In plus repairable becomes irreparable, right? So you have other words like in plus possible becomes impossible, right? We also need orthographic rules to develop a morphological parser. So we need three mainly: lexicon, morphotactics, and orthographic rules for developing a morphological parser. There are two challenges in developing a morphological parser. The challenge comes from morphotactics and the challenge comes from phonological alternations. From morphotactics, that is, we need to understand what suffix comes first, what suffix comes later, or what prefix comes first and what prefix later. That is the order of suffixes which attach to a word, or order of prefixes which attach to a word, etc. In fact, if you look at inflection and derivation, inflection attaches last to a word. That is, first you have a derivation and then inflection. Similarly, even within derivation suffixes attach in a particular manner. So if you have a word like pity, less can attach first and ness can attach next. That is, it can become pitilessness, is an English word, but it can never be pityness less, right? So less can attach to the word first, that is, it attaches to adjectives or nouns, and then it becomes adjective, then ness attaches to an adjective, right? That morphotactic rule we need to incorporate into our morphological parsers. That's a challenge. So we need to identify all the morphotactic rules first. Then phonological alternations are also important. Depending on the spelling, depending on the sounds in the word, the affixes change, the sounds of the affixes change, or the letters of the sound, the affixes will change. So if you look at a word like pity, pity, P-I-T-Y, it ends with the letter Y. But when a suffix like less attaches to it, Y becomes I in spelling. Similarly, a word like die, D-I-E, becomes D-Y when you attach ing or the present participle form of dying, right? When the present participle inflection attaches to the word die, it becomes dy. So this alternation also we need to take into consideration when we develop morphological parser. So these are the two challenges, particularly when we develop a morphological parser. Now, when we are developing a morphological parser, what is the model we are going to follow? One model which helps us, human morphological processing. When we try to understand how humans process morphology, then we may be able to develop a morphological parser for computers or for the systems which we are going to use, right? So look at how human morphological processing happens. In human morphological processing, a multi-morphemic word, that is, if it is single morpheme, then it can be stored as it is in the brain. But if it is a multi-morphemic word, how is it represented in the human brain? There are two ways. That means there are two hypotheses which we can have. One is full listing hypothesis, the other one is minimal redundancy hypothesis. In fact, we have already talked about this. We are going to revise that now. We are going to recall what we have said. When we say full listing hypothesis, we are going to list all the words in the brain. So what we are saying is, in the brain of human being, all the words of the language which he speaks are listed. But that's not possible. How can you list all the words? Which is untenable, because English doesn't have much inflection. But there are languages like Turkish, which is very highly inflected. Even Indian languages are highly inflected. For a particular word, there can be several forms of the word. Right? So it is expected that in Turkish there are 200 billion words. So how is the brain going to store all the words? Right? So it is impossible to say that human brain stores all the words of the language. Instead, if we say human brain stores stems and then the affixes, and there are rules which combine affixes with the stems. That is, we are reducing the redundancy. That is, each word is stored only once. Each stem is only once. We are not repeating it. Okay? So, for example, let's say if we have a word like keep. The word keep has different forms. Keep, keeps, kept, keeping. Right? Now, these four forms are not listed in the brain. What is listed is only the word keep as a stem, and the affixes s and ing are stored, or past tense morpheme is also stored in the brain. And there is a rule which combines the word keep with the affixes to get all the four forms. So we are reducing the redundancy. We are not storing the word keep 4 times. We are storing only once, and the morphemes attached to give us the output forms. What is the evidence for minimum redundancy hypothesis? We get evidence from 3 different forms: new singulars, new morphemes, and psycholinguistic evidence. When I say new singulars, there are new singular words which are always formed. We know that indices is the plural form of index, but there are people, and we are now using indice as also as a word. It can be a new singular. For the word indices, there can be a singular like indices. Indice. Or similarly, Homo sapiens is the plural form, which exists as a plural form, but we can also have a new singular Homo sapien. Right? When you are saying new singulars can be formed from plurals, that means there is a rule. These are not stored anywhere. Right? There is a rule which removes the plural morpheme and we get the stem. Okay? That means there is a regularization of a rule. Okay? Then we also have new morphemes formed in the language. Language is changing. How is language changing? That means there must be new words are formed, new morphemes are formed. Like if you say aholic, we know alcoholic is a word. From that word, in fact, in that word aholic is not affix at all. But from that word, people have taken aholic as a separate morpheme and added to other words like workaholic. A new word is formed. So aholic is a new morpheme which is formed. Similarly, the word gate is formed in words like Watergate, Fornigate, etc. And head is also as a separate morpheme which is formed, new morpheme like pothead, metalhead, tech head, gearhead. These are all new words formed with the affix head. Head has become a morpheme now. Right? Similarly, Mac, very famous McDonald's Mac, is a new morpheme, is a new prefix. It is used McMansion, McJob, right? Or McNews. These are all new words which are formed by taking Mac as a prefix. Right? New prefix is formed. This shows that all the words are not listed in the brain of a human being. Human brain has processes, morphological processes, morphological rules. So stems are listed, affixes are listed, new affixes may be formed to attach to the stems which are already existing, and new words are formed. Then we have psycholinguistic evidence. What is the psycholinguistic evidence? We have over-regularization. In fact, when someone is learning a language, or a child who is learning a language, before coming across the irregular form, the child uses the regular morpheme for constructing words. For example, you find a child using goad, or a learner, even a second language learner, using a word like goad. For the past tense of go, he may be using goad. Later he will learn went. So that means regularization is a process. That means using regular affixes, right, to form words is a process, right? In fact, goad doesn't exist. The word doesn't exist anywhere. In fact, the learner might not have heard the word goad at all, but he forms a new word, goad. How? By looking at word like talk, talked, close, closed. Then he looks, when he comes across the word go, he says go, goad. So ed is a regular suffix which is added to a verb to make a past tense. That's the rule which the learner forms, and then he produces a word like goad before he comes across the irregular form went. Similarly, he will say tooths instead of saying teeth, right? Or he may, in fact, in an experiment, Freiberg also got a data. He said he bitted me on my foot, right? Bitted, bite actually, past tense, but the child uses bitted me on my foot, or bited, right? This is over-regulation. So over-regularization shows that children are applying the rules. While applying the rules, they are acquiring the language. That means there are rules in the human brain, or there are rules formed in the human brain, not stored, not the words are stored. Other evidence is something from work tests, where an experiment was done. We know that English regular plural has three surface forms: z, s, and us. Right? Z, s, and us. So the plural morpheme is z, but allomorphs are z, s, and us. And how do children learn these rules? This was the experiment done. In that experiment, this is the test paradigm which is given. So children are presented with a pretend creature, right? Some creature which is pretended, and told this is a work. Something like this, let's say. This is a work. Then another work is revealed, another work is shown, and so the researcher says, now there are two of them. There are two and a blank. Very young children are baffled by the question and are unable to answer correctly, and responded to wug first. Okay? They're very young children. Children in grade 1 were almost fully competent with the regular plural. So they said two wugs. That is, both preschool and first grade children dealt poorly with us. They do not know us, but they have learnt s and z, so they use two words. Okay, this is an experiment. So the first experiment proved that young children have extracted generalizable morphological rules from the language around them. They have learnt the generalized rules first, right? This shows that words are not listed in human brain. Rules are formed from the linguistic evidence which the children are exposed to. Then another piece of psycholinguistic evidence comes from morphological errors. The kinds of errors which we make, either while learning or tongue slips, is like this: morpheme exchange. The word morpheme of one word is added to another. Instead of saying thinly sliced, slightly thinned. Okay, or thin slightly. No, right? Thinly sliced becomes slightly thinned. Or a feature is shifted, particularly the past tense form. Now, the past tense which is supposed to occur on the auxiliary is shifted to the main verb. Instead of saying had to go, we may quickly say have to went. Right? A tongue slip, an error. Or faulty access. Instead of saying have taught, have teaching. And instead of saying conclusion, concludement. Right? Meant is also noun, nominal suffix. Shun is also nominal suffix, but shun goes with certain verbs and meant goes with certain other verbs. But as an error, right, in fast speech, we may find some tongue slips and we find a word like concludement instead of conclusion. This shows that there are separate affixes and stems and they are combined in the brain when we are speaking. So morphological errors strengthen our second hypothesis. There is also another piece of psycholinguistic evidence which comes from lexical disorder or morphological disorder. There's a person, CSS, right, and he's 65 years old. Right, an experiment was done on this person by Badeker in 2001, and this person, CSS, suffered a left cerebrovascular accident in 1990, resulting in lexical impairments. That means there was some problems with his language, manifested in reading, repetition, and oral and written naming tasks. Yes, so he had a problem in reading, repetition, and oral and written naming task. When you are asked to name, he has problem, either oral or written. Apart from word finding problems, CSS spoken output is fluent. He was very fluent, and he exhibits no apparent comprehension impairment. So his comprehension is all right. He is able to understand, but only while repeating or naming or in reading he had a problem, right? So when he was given a word like a picture like butterfly, naming from definitions or given a definition, he was given a word like, he was asked to name the word. He was correct when it was monomorphism, 80% correct monomorphisms, right? But he was correct only 50% when it is polymorphism. That means when you say polymorphism, there are more than one morpheme and one morpheme attaches to another. That means there is a rule, right? So then there is a problem. So he had a problem. Dr. Fly, sun is okay when he has pronouncing monomorphic words 80%, or wheel pill is a monomorphic, right? So he was wrong, 50% wrong in producing polymorphisms or speaking, naming. With monomorphisms he had. So this shows that monomorphisms are stored as they are, But polymorphemes are stored separately. The morphemes are separately stored and they are combined by a rule. Right? Again, this piece of evidence strengthens our second hypothesis, right? Minimal redundancy hypothesis. So what do we conclude from this? We conclude that humans decompose words into morphemes and store them as such. Right? We store morphemes, not words. And both regular and irregular or restricted morphology involve rule-governed decomposition. Regular morphology is stored, even irregular morphology is stored as this. Okay? Then humans look for morphological structure even when there isn't. So when you are looking at a word like cheeseburger, there is no morpheme analysis involved. But we look at ER as a separate morpheme, though it is not a morpheme in this word. Similarly, in the word corner, we look at ER as a word. So corn plus ER possibly. Right? So we try to look for such morphological structure even when there is no morpheme existing in the word. Right? This shows that humans store morphemes, not words, in their brains. So human morphological processing tells us that when we develop morphological parser, we do not store all the words of a language in the machine. We have to store morphemes and we have to give the machine morphotactic rules, right? So what do we need for a morphological parser? In order to develop or in order to build a morphological parser, we need these three at least. A lexicon consisting of stems and affixes. Then morphotactics, the rules which combine the morphemes with the other morphemes. Then we also need orthographic rules, that is spelling rules. Right? Let's meet the next video.